For our system dynamics and vibrations project, we are going to explore the stability of an inverted pendulum mounted to an oscillatory base. For our base, we are using a reciprocating saw that has been mounted upside down to a table. In order to take a look at why this phenomenon happens, we derived the equation of motion for this system. For this, we're going to use a method not taught in class. It's the Euler-Lagrange equation. And this here is the angular form of that. And here's the diagram of the system. You can see that the point the pendulum is attached to is going to be moving up and down with sinusoidal motion. Our first step is to find the kinetic energy of the mass at the end of the pendulum. And now that we've found the kinetic energy, we can quick find the potential energy. And L is just kinetic minus potential. Now that we have the Lagrangian term, we can find the two components of the Euler-Lagrange equation. Plugging these two components in and setting it equal to 0, and you can see a lot of terms cancel. And since this is the forcing term, we can put it onto the other side. So there we have derived our governing equation. So now that we solved for a differential equation, we were able to use MATLAB to simulate the system. We solved for theta double dot, and you can see here's a code that we found in Wikipedia that gives us the breakdown of the differential equation, and we used the ODE 45 function to solve the differential equation in MATLAB. We then graphed the result of the system at different lengths. In order to model our system correctly, we actually did take the frames that it took to do one oscillation. We were able to find that it's running at about 48 hertz. And we also measured the amplitude of the reciprocating saw. At about half a meter, you can see it's fairly stable and it's fairly slow oscillations. The simulation, we're giving it a slight input, so it is starting at an offset. And then as the length decreases, it starts to oscillate at quicker and quicker, or higher and higher frequencies. Here's 5 centimeters, and then at 4 centimeters, it's also oscillating at larger and larger amounts. So this is about 20 to negative 20 degrees. And then at 3 centimeters, it becomes unstable and just starts to spin around in circles. So according to our MATLAB simulation, somewhere between 4 centimeters and 3 centimeters is where it becomes unstable.
In order to see if our MATLAB simulation was accurate, we experimented with shorter and shorter pendulums to see if they were stable. This is the 9.5 centimeter pendulum, the 6.5 centimeter, the 5 centimeter, the 3 centimeter, and lastly we tried with the 16 millimeter pendulum, but even that one was really stable. One of the sources for inaccuracy in the simulation is that we assumed that the pendulum bar was massless, but in our experiment we had mass in the bar.
Another factor that may have added to the additional stability that we saw in the real-world test is the friction between the pendulum and the base, which is not insignificant.